So a moment ago I said that the energy of each photon was small because something times 10 to the minus 19th joules looks trivial. But let's put that number in more context. If you look at the average kinetic energy of molecule of, I think I did this for nitrogen at 25 degrees C, the kinetic energy of that nitrogen is only about 3.7 kilojoules per mole. Again, I'm using the mole basis because it's easier for me to wrap my head around it. Now, visible light, we said was, I don't remember what the number was, 400, something like that. So it's over 100 times the energy in a single gas molecule. And what that means is that when visible light interacts with biological molecules, it has sufficient energy to put those molecules into very different configurations than they are at rest. Are you with me? Think, for example, again, by way of analogy, think of a clock, a wind-up clock, an old grandfather clock. If you consider the energy just in the molecules of air around the key in the clock, the energy in those gas molecules, well, it's equal on both sides, isn't it? So the pressure is equalized. The point that I'm trying to make is that it's so low that that grandfather clock is not going to wind up in and of itself. But if you apply your hand to it, you can apply force, and you have a significant amount of energy there concentrated in one place. The analogy that I'm trying to make is that a photon impinging on the right type of biological molecule has a lot more energy than the gas molecules around it, and can, if you will, wind those biological molecules into much higher energy states than they would otherwise be. Now, having said that, and maybe the analogy is David with his device there that catches my baseball. So I'm going to throw, and it spins right as I throw these things, sort of water wheel thing. Now, there can be too much of a good thing. David wants to make a lot of power, so I start throwing more of these, right? But he says, no, this isn't enough. Why don't you just throw a lot faster? So I can't, but I get somebody here who's played a lot of baseball to start throwing the balls, and he's throwing the balls twice as fast, 4 times the kinetic energy, and what happens to David's device? It breaks. It's not meant to capture a 70-mile-an-hour baseball. It can only deal with a 30-mile-an-hour baseball, right? Huge difference in energy. So the same analogy, the analogous situation holds for photosynthesis. UV photons actually can contain sufficient energy to break certain covalent bonds. Now, if you're running a disinfection system at a water treatment plant, you're going to use that principle to disinfect water, because you're going to have high intensity discharge, ultraviolet bulbs, and the water is going to go through a thin, a narrow area so that all the water is exposed essentially to the same intensity light, and it's in there for long enough that you kill 99.99999% of all the organisms there. Okay, very good. But that same effect, if you put your hand in there, or we don't do silly things like that, but if you go outside and expose yourself to sufficient ultraviolet without proper protection, you run the risk, I mean, it's a roll of the dice. You run the risk that one of those photons is going to interact with DNA in your skin cells in such a way as to affect change that causes cancer. All right? Now, that you won't do with infrared light or with visible light. You can spend all the time you want in visible light or longer wavelengths, and you're not going to have sufficient energy to cause that break. And again, think of David's wheel here. I may increase the frequency, but even at high frequency, I don't have sufficient energy in one of those baseballs to actually crack the arm of his catching device. All right? So the wavelength becomes very important. So if you're interested in capturing solar energy, and that's really what we're talking about here. The intensity of the light that you're capturing is the figure of merit, if you will. It's what you're interested in. And typically what we look at is the energy per unit time, per unit area, or the power per unit area is the way we'd say that. And the most common way of reporting that is the watt per square meter. All right? If you go to the very top of the atmosphere and you look at the incident sunlight, so here we are, here's the top of the atmosphere, and we look at the incident sunlight perpendicular to the rays of the sun, you'll get about 1,370 watts per square meter across all wavelengths. Okay? That includes the so-called photosynthetically active radiation, or PAR, and the infrared, ultraviolet, and everything else. At the Earth's surface, a lot of it's gone. I mean, 570 watts per square meter or so has disappeared. Hasn't really disappeared. It's been absorbed in different ways, and it's doing interesting things like making the wind blow, driving the hydrologic cycle and whatnot. So you might get 800 watts per square meter on a bright sunny day. Again, that's for all light, all electromagnetic radiation from the sun, not just photosynthetically active radiation. Surface of the Earth, if you're looking at 420 or so watts per square meter as the maximum photosynthetically active radiation fraction. All right, so a little more than half of that 800. Okay, these are good numbers to sort of have some feeling for. So we can also express the intensity in terms of the number of photons per unit time per unit area. And we call that the photon flux density, or PFD. More commonly, we talk about the photosynthetically active portion of that, the photosynthetically active photon flux density. And don't ask me why it's not PAPFD, it's not, but PPFD is the notation that's used. So now, if you see PPFD, you say that's photosynthetically active photon flux density, and it's typically given in this type of unit, micromoles per square meter per second. All right? And you might max out around 2,000 on the Earth's surface for PPFD. If you want to cross-check that and see how that relates to what I tell you, I said 420 watts per square meter in photosynthetically active radiation. If you want to see what kind of average wavelength this 2,000 micromole per square meter per second is, you can use this equation. This is the interrelationship between micromoles per square meter per second and watts per square meter. It's how much energy is there per photon. All right? They're just two alternate ways of examining the same thing.